Okay, so here is like a short outline for the presentation. I start with a very brief introduction to data-centric manufacturing, then a couple of slides about extra high voltage cable manufacturing. I hope it's mostly like known to all of you, but to get everybody on the same page. Then I present a topography scanner, which is a device made by our company. It's a device for continuous quality measurement in high voltage and extra high voltage manufacturing. Then we jump into smart buffering, which is another product by Maillefer, and this is like an autonomous process controller for fiber optics manufacturing. And I end the presentation to short kind of a wrap-up of the presentation. So the transition towards data-centric manufacturing, well, data has always been there. So it's the contexts of the data that is now changing. So data has been traditionally in very small contexts. For example, like one sensor, PID controller, and one actuator, but it's based on data. So now the transition is more towards like acquiring data from multiple different sources, getting a more holistic view of the data, and then taking like more intelligent actions than were previously possible. That of course enables many new things that can be done. Kind of challenge here is that the traditional systems do not natively support this. But as with all the kind of system sciences, abstraction is the key. And what we need is another layer of abstraction on top of the old ones. So in a sense, we can keep more or less the PLC and SCADA world as they are, just connect to them and then build more intelligence above those layers. And what this enables then is what I just said, is that we can have multiple different data sources and process them holistically and then create new services and products. So it's the analytics and intelligence layer which is kind of the key driver here. This was the short presentation from the data side, and let's jump into extra high voltage cable manufacturing and its kind of special peculiarities. So why we make extra high voltage cables? It's because the higher the voltage inside a conductor can be, the less there will be energy loss. And actually the energy loss in power transmission accounts for a quite substantial amount of energy loss like worldwide. So pushing the limits in the voltage that can be put inside one conductor helps in kind of saving energy. And now with the green energy, the transition towards solar and wind power, this is of course a big driver in this power cable manufacturing scene. And for that, when you want to make like extra high voltage cables, you need very special equipment and dedicated process controls and know-how. Typically the factories are, as you see in the smaller picture, located close to the sea because you want to get the cable directly to the ship, which is then used to install the cables. And how we make those cables? Well, one of the key processes is the continuous vulcanization process. It is the first kind of process that is applied for the conductor. So in the continuous vulcanization process, we make the first 3 layers on top of the conductor. The inner semiconductor, the insulation layer, and the outer semiconductor. And the idea is to use those layers to confine the flow of the current inside the conductor so that no power breakthroughs will occur. Typically they are made in vertical CV lines. Vertical because it's easier to control the roundness of the cable. When it's kind of soft and melty, it's keeping the form easier because the gravitation is not affecting it. One peculiarity of the process is that it's very slow. The process runs typically at 1 to 2 meters per minute. And the towers are high and the lines are long. Well, everybody can understand that quality control here is also very important. Nobody wants to break a cable when it's been installed to the bottom of the sea. It's very costly. So, of course, quality control is done at multiple stages during the process, but whenever it can be improved, typically customers want to do this. And well, there's also like with better quality control, lots of room for kind of reducing the wasted materials and so on. And for the quality control, especially like continuous quality control of the CV process, we have developed this topography scanner device. And a conceptual view to the device is that it's equipped with from 5 to 8 laser sensors, laser line triangularization sensors on all sides of the cable, so that when we do sensor fusion for the data, we get kind of a complete view of the cross-sectional shape of the cable. So one measurement it produces is kind of the shape of the cable. On the left here we have like a not so good cable, and there is a better cable. Of course, it's not that bad in reality. Here the scale is exaggerated. For example, one step in the scale can be like 1 millimeter. So the variations are really small, but nevertheless we are aiming to perfectly round cables and try to minimize the variation in the shape of the cable. And when we take multiple of these cross-sectional shapes, something like from 800 Hertz to almost 3000 Hertz. So when we take multiple of those measurements in succession, we get the whole 3D map of the cable surface. So in those bottom pictures, we have the cable surface opened up as a plane. And the left one also there looks a little bit more rough, so there are bumps and waviness on the surface, which is caused mainly by the extruder, rotating extruder, which in a way pulses a little bit the mass towards the cable. But by optimizing the parameters, we can move towards the right hand side of the surface, so less wavy, less bumpy. And what is like a kind of a big thing here is that when we get the surface data for the cable, we can use that as an input for finding automatically possible defects on the cable surface. So the topography scanner is equipped with an automatic defect detection system which continuously scans the cable surface by looking for anomalies. So it's able to spot scratches, bumps, whatever is like abnormal on the cable surface. And to make it usable in practice, we have developed kind of a classification system. So in practice there are lots of anomalies on the cable surface which are not critical for the cable insulation properties. There are byproducts from the process which are kind of attached to the surface but which are not critical. So we need to have we have developed a system which is based on convolutional neural network classification, and it's able to classify the found defects on cable surface to 14 different classes. And out of those, the operators or the process manager is able to select which classes at which dimensions are considered critical and which are not, and just saved to a database. And actually also the information about, for example, the type and class of the byproducts is also important. That is a very good input for predictive maintenance purposes. If we start to get an increase in byproducts at certain side of the cable, then it's of course kind of a good hint on where to look and what to fix. This is just, I don't know if you are able to see the small pictures, but examples of the different classes the system is able to classify the defects. Here the three-dimensional data is projected into two dimensions, and the height is presented in grayscale values. So what we are looking especially are like scratches and scorches. Scorches are like burned material, which is penetrating inside the cable. So scratches and scorches, if they are deep enough, then they are of course critical for the insulation properties, and in the end you have to cut that part out of the cable and make an additional joint, which is never nice, but it's better than having the kind of defect go unnoticed further in the process. Okay, this is kind of the future target we aim with the topography scanners. So ideally, because we get the continuous data from the process, we would of course like to link that back to the process control. So when we see that something was not right, then we would like to automatically or semi-automatically adjust the process and fix, for example, the roundness or the waviness of the cable, so that we are always going towards the better product. And this is something that we are currently working quite a lot, but there are challenges. So ideally, well, this is a very far-going vision. Let's get back to it a little bit later. But now, starting with the simple feedback or control loop that is based on data by the topography scanner. About this picture, the key thing to notice is that the extruders are very high or in the beginning of the line. Then the cable goes through the vulcanizing chambers, and it acquires its final form when it's as cooled down enough. So the topography scanner is usually located quite in the end of the line. And the process was slow, moving about 1 to 2 meters per minute, and the lines are long. So if we want to do a control loop, it will be very slow, like doing adjustment, waiting 2 hours, seeing how they affected, doing adjustments, waiting again like 2 hours. So it's possible, but it's very slow. Another challenge is that nobody wants to ruin the cable. They are typically run like 2-week production runs, and usually so that we use pre-calculated recipes, and when a recipe is found to be good, nobody touches the parameters. We just run with the same recipe. So how can we develop the process if the kind of process window, the variation in the process parameters is very small and the control loop is very kind of big or slow? That we have been thinking. If somebody has good ideas, I'm eager to hear them. Well, in order to develop the autonomous process control, we are working in parallel with the fiber optics lines. So in order to kind of get experience with the automatic process control and also to develop kind of the foundations for it, we have already developed a system for the buffering process, which is a sub-process in fiber optics cable production. So this process is about creating a protective tube around a bundle of fibers and some filling material. And this is, if compared to the CV process, this is a fast process, around 500 to even 1,000 meters per minute. So if we do adjustments, we don't need to wait just like maybe 30 seconds to see the effect of the parameter adjustment to the product. But here, like one of the challenges is that the main or one of the main end quality parameters that we need to kind of optimize is the attenuation, which is how much the signal weakens when it's going through the whole cable. And that is something that can be measured only after the kind of product has been finished. So we have needed, or it has been required that we devise a system where we can feed the end quality measurements afterwards to the system, and then we link it like in a delayed manner to the process parameters. It is working, and it's nice. Actually, with this process, originally our idea was to create only a prediction system for the end quality parameters, because it's not possible to measure them on the run, the attenuation values, for example. So our original idea was to just use process data and then do like different neural network predictors to predict the end quality values. But We did some data analysis for such lines at our customers, and from the data we saw that, well, it's not going to be possible because how the operators operate the line is so messy. Some are operating very nicely, they do good products. Some are doing the complete opposite, they are messing everything up. Most of the people do something in between, sometimes good cables, sometimes not so good, and they do it in such many ways that in the end we had a mixture of kind of process settings producing a mixture of outputs, and nobody could make any sense out of that. So after showing from the data how the humans operate the line, we went directly to implement this autonomous process controller. We saw that humans cannot operate the line how it should be operated, so let's make a kind of computer system to operate the line. And in the end, after the kind of we started working with this automatic system, predicting the end quality became also much easier because it was done in a way deterministically, always in a similar fashion, the process control. And well, about this system, it's able to optimize the process on the fly to desired end quality properties. It also has this predictive maintenance or guided maintenance functionality. So when the process cannot be optimized or it encounters some problems, it's able to pinpoint for the operators what is not working on the line. Is it in the beginning of the line something that you need to check, or in the end of the line? And so it's helping the operators. And the design is completely like a system on the edge, so it doesn't need to be connected to any cloud services. It's in a way a small industrial PC that's just attached to the line. It reads data from the line, does its analysis and takes decisions and writes control parameters back to the line. And here is actually some data from a customer site. So here this is from a half a year, 6 months period, and the individual gray dots represent one production run, and there are quite many of those. You can see the kind of gaps there. They were not running during the weekends at this time, so all the runs are, at least on the left side, concentrated during the week. And the y-axis is attenuation delta. This is a value we use to evaluate the performance of the buffering process. So how much increase in attenuation the fibers get during the buffering process. For all fibers, we know the initial attenuation when they come from the kind of a fiber factory, and then the attenuation is measured after the buffering process, so we know how much it's been increased. So after we initially this was the first time we put the system in operation for long periods of time. So initially it was quite high. Then when we found good parameters and adjusted them on the fly for some time, then we were almost able to cut down to half the increase in attenuation that the system was causing. There are some spikes in the data. These we were able to identify that bearings of one pulling device were broken, and now it's able to predict it on the fly. These are most likely some kind of operational errors by humans. They were happening during the vacation period, so probably somebody just made some incorrect kind of setup for the line when they were changing products. We are not completely sure because we don't have data from that. But anyways, the data shows that the system works, and it's basically completely autonomous. After they have set up the line, put in the materials, they just kind of activate the line, and the system takes care of everything. So the first completely autonomous cable production line. Okay, the same old slide you saw earlier. I presented briefly the topography scanner and the smart buffering system. We also have different kind of technologies which fit into this big picture. And the idea is that, well, we have this aim of a kind of a MyLefer data center that could be used to gather and automatically analyze data and send updates for softwares or kind of automatically maybe control systems. Not necessarily in the beginning completely centralized, but at least like a local data center for each customer, so that they could benefit if they have topography scanners in multiple lines around the globe. Then if they kind of find good improvements to some product, then it would be easy, immediately distributed to other lines. And for example, this online curing control is a system which tries to optimize the roundness of the cable. And that is one thing that we are aiming now to connect with the topography scanner, but the challenge is, as I said earlier, the slowness of the feedback loop. Cloud NCC is a cloud version of our modeling and simulation tool that is used to kind of design CV lines and calculate recipes for different products. It has traditionally been shipped as a standalone program, but we are now kind of shifting the thinking of our customers into more cloud-like approaches by presenting the software in the cloud. And of course, that offers us also many advantages, because collaboration with the customers is easier, and we also see like what kind of things they are exploring with the tool, which helps us to kind of create our products and also the software and so on. So in a way, this slide tries to summarize what is meant for us by the transition towards data-centric manufacturing. It's not one big thing that is happening by itself, but it's many small things that we are kind of putting as pieces of a puzzle to the same big picture. And necessarily, or it might be that some of the pieces do not fit in the end, but at least they are now being worked on to the big picture, and we get knowledge about how things work, and we are slowly moving towards the kind of a future target, which would be this kind of AI-driven automation and the smart factory concept. So we have already seen with the smart buffering that humans make very suboptimal decisions when they are given the kind of a responsibility of the process. Computers work 24/7. They can see much larger contexts on the data, so why not replace humans in that duties with computers when it's possible? And the legacy systems, cable factories can be operational for decades after they have been purchased, so we have to live together with the old systems, and in a way abstraction layers just need to be increased on top of the old ones. And well, with the legacy systems, the interesting thing is that we have to remember that the decisions that we make today will be the legacy systems of the future. So the responsibility is, in a way, quite great. And well, that I also already mentioned, that we are simultaneously working on different domains to make this transition to data-centric systems in parallel. And one kind of important thing is this kind of a change management, but we are probably even not yet there. It's kind of shifting the human thinking towards that machines or computers can do certain things much better than the humans. So shifting the thinking both at customer side, but also like inside our own company. We have to kind of get rid of the old proven like concepts and base the actions on data. So maybe one day we can really say that we have implemented something in the domains of AI-driven automation and the smart factory concept. Thank you. If there's any question, I'm willing to take them now, or if you have some ideas on the speeding up the optimization loop on the CV lines, I can take that in more depth and detail on some breaks. But
just what has been the feedback from the market so far on, for example, your buffering line?
The feedback has been very positive. In speech, we have not received that many orders, so it's still in a way in evaluation at one of our customers' site where it's working correctly, but they are kind of gathering money to be able to install it to other lines, and that's actually we have been able to sneak into that customers because now they have it in one line and it makes the operation so much easier. They have a couple of other similar lines without the system, and now they cannot exchange operators from the kind of new line to the old line because they don't know how to operate the old lines without the system. So I'm quite sure they need to order more in the future.
The edge computer is off the shelf. It's
Yes.
custom made. Okay.
Yeah.
What is proprietary is the software running it.
Yes.
Okay.
Yeah.
What do you use out of curiosity? Siemens or?
Yeah, our own lines are kind of a Siemens PLC, but the system is agnostic. So
Yeah, but the edge computer. Do you have
the edge computer is basically a Windows PC with a custom software inside.
Okay, but it runs Windows. Okay.
Yeah. It's running Windows because our line control computers also run Windows, so our engineers are more accustomed to work with Windows, so it's easier than that all the computers are Windows. Otherwise, it wouldn't matter. All right, thank you.